In music, just intonation, sometimes abbreviated as G, or pure intonation, is any musical tuning in which the frequencies of notes are related by ratios of small whole numbers. Any interval tuned in this way is called a pure just interval. Pure intervals are important in music because they correspond to the vibrational patterns found in physical objects which correlate to human perception. See harmonic series. The two notes in any just interval are members of the same harmonic series. Frequency ratios involving large integers such as 1024, 729 are not generally said to be justly tuned. Just intonation is the tuning system of the later ancient Greek modes as codified by Ptolemy. It was the aesthetic ideal of the Renaissance theorists, and it is the tuning practice of a great many musical cultures worldwide, both ancient and modern. Quote, just intonation can be contrasted and compared with equal temperament, which dominates Western instruments of fixed pitch, e.g., piano or organ, and default MIDI tuning on electronic keyboards. In equal temperament, all intervals are defined as multiples of the same basic interval. Or more precisely, the intervals are ratios which are integer powers of the smallest step ratio. So two notes separated by the same number of steps always have exactly the same frequency ratio. However, except for doubling of frequencies, one or more octaves, no intervals are exact ratios of small integers. Each just interval differs a different amount from its analogous equally tempered interval. Justly tuned intervals can be written as either ratios with a colon, for example, 3, 2, or as fractions with a solidus, 3 halves, for example, 2 tones, one at 300 Hz cycles per second, and the other at 200 Hz, are both multiples of 100 Hz and as such members of the harmonic series built on 100 Hz. Thus 3, 2, known as a perfect fifth, may be defined as the musical interval, the ratio between the second and third harmonics of any fundamental pitch. Audio examples: just intonation and A major scale, followed by 3 major triads, and then a progression of fifths in just intonation. Equal temperament and A major scale, followed by 3 major triads, and then a progression of fifths in equal temperament. By listening to the above file, and then listening to this one might be able to hear the beating in this file. Equal temperament and just intonation compared a pair of major thirds, followed by a pair of full major chords. The first in each pair is in equal temperament. The second is in just intonation. Piano sound. Equal temperament and just intonation compared with square waveform a pair of major chords. The first is in equal temperament. The second is in just intonation. The pair of chords is repeated with a transition from equal temperament to just temperament between the two chords. In the equal temperament chords, a roughness of beating can be heard at about 4 Hz and about 0.8 Hz. In the just intonation triad, this roughness is absent. The square waveform makes the difference between the equal and just temperaments more obvious. History. Pythagorean tuning. Perhaps the first tuning system to be theorized in the West is a system in which all tones can be found using powers of the ratio 3, 2, an interval known as a perfect fifth. It is easier to think of this system as a cycle of fifths, because a series of 12 fifths with ratio 3, 2 does not reach the same pitch class it began with. This system uses a Wolf fifth at the end of the cycle to obtain its closure. Quarter comma mean tone obtained a more consonant tuning of the major and minor thirds. But when limited to 12 keys, see split keys, the system does not close, leaving a very dissonant diminished sixth between the first and last tones of the cycle of fifths. In Pythagorean tuning, The only highly consonant intervals were the perfect fifth and its inversion, the perfect fourth, the Pythagorean major third, 81, 64, and minor third, 32, 27, were dissonant, and this prevented musicians from using triads and chords, forcing them for centuries to write music with relatively simple texture. For instance, if one decreases by a syntonic comma, 81, 80, the frequency of E, C, a major third, and e.g., a minor third, become just, namely, CE is flattened to a justly intonated ratio of 81, 64, times 80, 81, equals 5, 4, and at the same time e.g. is widened to the just ratio of 32, 27, times 81, 80, equals 6, 5. The drawback is that the fifths A and EB, by flattening E, become almost as dissonant as the Pythagorean wolf fifth, but the fifth CG stays consonant, since only E has been flattened. CE times EG equals 5, 4, times 6, 5, equals 3, 2, and can be used together with CE to produce a C major triad. CEG. By generalizing this simple rationale, Gioseffo Zolino, in the late 16th century, created the first justly intonated seven-tone diatonic scale, which contained pure perfect fifths, 3, 2, pure major thirds, and pure minor thirds, FACEGBD. This is a sequence of just major thirds, M3, ratio 5, 4, and just minor thirds, M3, ratio 6, 5, starting from F plus M3 plus M3 plus M3 plus M3 plus M3 plus M3. Since M3 plus M3 equals P5, perfect fifth, I, E, 5, 4, asterisk, 6, 5, equals 3, 2. This is exactly equivalent to the diatonic scale obtained in 5-limit just intonation. The Kuchen has a musical scale based on harmonic overtone positions. The dots on its soundboard indicate the harmonic positions: 1/8, 1/6, 1/5, 1/4, 1/3, 2/5, 1/2, 3/5, 2/3, 3/4, 4/5, 5/6, 7/8. Diatonic scale. It is possible to tune the familiar diatonic scale, a chromatic scale, in just intonation in many ways, all of which make certain chords purely tuned and as consonant and stable as possible, and the other chords not accommodated and considerably less stable. The prominent notes of a given scale are tuned so that their frequencies form ratios of relatively small integers. For example, in the key of G major, the ratio of the frequencies of the notes G to D, a perfect fifth, is 3, 2, while that of G to C, a perfect fourth, is 4, 3. 3 basic intervals can be used to construct any interval involving the prime numbers 2, 3, and 5, known as 5-limit just intonation. 16, 15 equals S, semitone. 10, 90 equals T, minor tone. 09, 80 equals T, major tone, which combine to form 6, 5 equals TS, minor third. 5, 4 equals TT, major third. 4, 3 equals TTS, perfect fourth. 3, 2 equals TTTS, perfect fifth. 2, 1 equals TTTTTSS, octave. A just diatonic scale may be derived as follows. Suppose we insist that the chords FAC, CEG, and GBD be just major triads. Then ACE and EGB are just minor triads. But DFA is not. Then we obtain this scale. Ptolemy's intense diatonic scale. The major thirds are correct, and 2 minor thirds are right. But DF is a 32/27 semi-detone. Others approaches are possible. C5 limit tuning. But it is impossible to get all 6 above-mentioned chords correct. Concerning triads, the triads on I, IV, and V are 4, 5, 6. The triad on E is 27, 32, 40. The triads on E and V are 10, 12, 15. And the triad on VII is 45, 54, 64. For or justly tuned minor scale, 2 of the steps must be switched to obtain optimal minor thirds. C5 limit _ tuning. Another variant, C5 limit tuning below, uses the minor tone of 10/9 and gives the minor seventh a ratio of 16:9 equals 1.778 instead of 9/5, which is closer to the equal temperament tuning of 1000 cents i.e. a ratio of 210/12 equals 17,818. But then major and minor thirds including this tone are out of just intonation. 12-toned scale. There are several ways to create a just tuning of the 12-toned scale. Pythagorean tuning. The oldest known form of tuning. Pythagorean tuning can produce a 12-toned scale, but it does so by involving ratios of very large numbers, corresponding to natural harmonics very high in the harmonic series that do not occur widely in physical phenomena. This tuning uses ratios involving only powers of 3 and 2, creating a sequence of just fifths or fourths, as follows. The ratios are computed with respect to C, the bass note. Starting from C, they are obtained by moving 6 steps around the circle of fifths to the left and 6 to the right. Each step consists of a multiplication of the previous pitch by 2/3. Descending fifth, 3/2. Ascending fifth, or their inversions, 3/4 or 4/3. Between the enharmonic notes at both ends of this sequence is a difference in pitch of nearly 24 cents, known as the Pythagorean comma. To produce a 12-toned scale, one of them is arbitrarily discarded. The 12 remaining notes are repeated by increasing or decreasing their frequencies by a power of 2, the size of 1 or more octaves. To build scales with multiple octaves, such as the keyboard of a piano. A drawback of Pythagorean tuning is that one of the 12 fifths in this scale is badly tuned and hence unusable. The Wolf fifth, either F sharp D flat if G flat is discarded, or B G flat if F sharp is discarded. This 12-toned scale is fairly close to equal temperament, but it does not offer much advantage for tonal harmony because only the perfect intervals, fourth, fifth, and octave, are simple enough to sound pure. Major thirds, for instance, receive the rather unstable interval of 81/64 sharp of the preferred 5/4 by an 81/80 ratio. The primary reason for its use is that it is extremely easy to tune. As its building block, the perfect fifth is the simplest and consequently the most consonant interval after the octave and unison. Pythagorean tuning may be regarded as a 3-limit tuning system, because the ratios are obtained by using only powers of n, where n is at most 3/4 mean tone. The quarter-comma mean tone tuning system uses a similar sequence of fifths to produce a 12-tone scale. However, it flattens the fifths by about 5.38 cents with respect to their just intonation, in order to generate justly tuned major thirds, with interval ratio 5/4. Although this tuning system is based on a just ratio 5/4, it cannot be considered a just intonation system, because most of its intervals are irrational numbers. i.e., they cannot be expressed as fractions of integers. For instance, the ratio of most semitones is s equals 8.55 quarters. The ratio of most tones is t equals square root 5. 2. The ratio of most fifths is p equals 4 square root 5. 1. 5. Limit tuning. A 12-toned scale can also be created by compounding harmonics up to the fifth, namely, by multiplying the frequency of a given reference note, the bass note, by powers of 2, 3, or 5, or a combination of them. This method is called 5-limit tuning. To build such a 12-tone scale, we may start by constructing a table containing 15 pitches. The factors listed in the first row and column are powers of 3 and 5, respectively, e.g., 1/9 equals 3 minus 2. Colors indicate couples of inharmonic notes with almost identical pitch. The ratios are all expressed relative to C in the center of this diagram. The bass note for this scale. They are computed in 2 steps. For each cell of the table, a bass ratio is obtained by multiplying the corresponding factors. For instance, the bass ratio for the lower left cell is 1/9 times 1/5 equals 1/45. The bass ratio is then multiplied by a negative or positive power of 2, as large as needed to bring it within the range of the octave starting from C. From 1 to 2, 1. For instance, the bass ratio for the lower left cell, 1/45, is multiplied by 26, and the resulting ratio is 64/45, which is a number between 1 and 2. 1. Note that the powers of 2 used in the second step may be interpreted as ascending or descending octaves. For instance, multiplying the frequency of a note by 26 means increasing it by 6 octaves. Moreover, each row of the table may be considered to be a sequence of fifths, ascending to the right, and each column a sequence of major thirds, ascending upward. For instance, in the first row of the table, there is an ascending fifth from D and A, and another one, followed by a descending octave from A to E. This suggests an alternative but equivalent method for computing the same ratios. For instance, one can obtain A, starting from C, by moving one cell to the left and one upward in the table, which means descending by a fifth and ascending by a major third. 2/3 times 5/4 equals 10/12 equals 5/6. Since this is below C, one needs to move up by an octave to end up within the desired range of ratios. From 1 to 2, 1. 5/6 times 2/1 equals 10/6 equals 5/3. A 12-toned scale is obtained by removing one note for each couple of enharmonic notes. This can be done in at least 3 ways, which have in common the removal of G-flat, according to a convention which was valid even for C-based Pythagorean and quarter-comma mean tone scales. Note that it is a diminished fifth, close to half an octave, above the tonic C, which is a disharmonic interval. Also, its ratio has the largest values in its numerator and denominator of all tones in the scale, which make it least harmonious. All reasons to avoid it. We show here only one of the possible strategies. The others are discussed in 5-limit tuning. It consists of discarding the first column of the table, labeled 1/9. The resulting 12-toned scale is shown below. Extension of the 12-toned scale. The table above uses only low powers of 3 and 5 to build the bass ratios. However, it can be easily extended by using higher positive and negative powers of the same numbers, such as 52 equals 25, 5 minus 2 equals 1/25, 33 equals 27, or 3 minus 3 equals 1/27. A scale with 25, 35 or even more pitches can be obtained by combining these base ratios. C5 limit tuning for further details. Indian scales. In Indian music, the just diatonic scale described above is used, though there are different possibilities. For instance, for the sixth pitch, DHA, and further modifications may be made to all pitches excepting SA and PA. Some accounts of Indian intonation system cite a given 22 rootus. According to some musicians, one has a scale of a given 12 pitches and 10 in addition. The tonic, Shadja, SA, and the pure fifth, Pancham, Pa, are inviolate. Where we have two ratios for a given letter name, we have a difference of 81, 80, or 22 cents, which is known as the syntonic comma. One can see the symmetry, looking at it from the tonic, then the octave. This is just one example of explaining a 22-rooty scale of tones. There are many different explanations. Practical difficulties. Some fixed just intonation scales and systems, such as the diatonic scale above, produce Wolf intervals. The above scale allows a minor tone to occur next to a semitone, which produces the awkward ratio 32:27 for DF. And still worse, a minor tone next to a fourth giving 40:27 for DA. Moving D down to 10:9 alleviates these difficulties but creates new ones. DG becomes 27:20, and DB becomes 27:16. One can have more frets on a guitar to handle both as 9/8 with respect to G and 10/9 with respect to G, so that AC can be played as 6/5 while AD can still be played as 3/2. 8 and 10/9 are less than 1/53 of an octave apart. So mechanical and performance considerations have made this approach extremely rare, and the problem of how to tune chords such as C, E, G, A, D is left unresolved. For instance, A could be 4/3 below D, making it 9/8, if G is 1, or 4/3 above E, making it 10/9, if G is 1, but not both at the same time. So one of the fourths in the chord will have to be an out-of-tune Wolf interval. However, the frets may be removed entirely. This, unfortunately, makes in-tune fingering of many chords exceedingly difficult, due to the construction and mechanics of the human hand, and the tuning of most complex chords in just intonation is generally ambiguous. Some composers deliberately use these Wolf intervals and other dissonant intervals as a way to expand the tone color palette of a piece of music. For example, the extended piano piece is The Well-Tuned Piano by Lamonti Young, and The Harp of New Albion by Terry Riley use a combination of very consonant and dissonant intervals for musical effect. In Revelation, Michael Harrison goes even further, and uses the tempo of beat patterns produced by some dissonant intervals as an integral part of several movements. For many instruments tuned in just intonation, one cannot change keys without retuning the instrument. For instance, if a piano is tuned in just intonation intervals and a minimum of Wolf intervals for the key of G, then only one other key, typically E-flat, can have the same intervals, and many of the keys have a very dissonant and unpleasant sound. This makes modulation within a piece, or playing a repertoire of pieces in different keys, impractical to impossible. Synthesizers have proven a valuable tool for composers wanting to experiment with just intonation. They can be easily retuned with a microtuner. Many commercial synthesizers provide the ability to use built-in just intonation scales or to program your own. Wendy Carlos used a system on her 1986 album Beauty and the Beast, where one electronic keyboard was used to play the notes. and another used to instantly set the root note to which all intervals were tuned, which allowed for modulation. On her 1987 lecture album Secrets of Synthesis, there are audible examples of the difference in sound between equal temperament and just intonation, singing and unfretted stringed instruments. The human voice is among the most pitch-flexible instruments in common use. Pitch can be varied with no restraints and adjusted in the midst of performance, without needing to retune. Although the explicit use of just intonation fell out of favor concurrently with the increasing use of instrumental accompaniment, with its attendant constraints on pitch, most a cappella ensembles naturally tend toward just intonation because of the comfort of its stability. Barbershop quartets are a good example of this. The unfretted stringed instruments from the violin family, the violin, the viola, the cello and the double bass, are quite flexible in the way pitches can be adjusted. Stringed instruments that are not playing with fixed pitch instruments tend to adjust the pitch of key notes such as third and leading tones so that the pitches differ from equal temperament. Western composers' music written in just intonation is most often tonal but need not be. Some music of Craig Grady and Daniel James Wolfe uses just intonation scales designed by E.R.V. Wilson explicitly for a consonant form of atonality, and Ben Johnston's Sonata for Microtonal Piano, 1964, uses serialism to achieve an atonal result. Composers often impose a limit on how complex the ratios used are. For example, a composer may write in 7 limit G, meaning that no prime number larger than 7 features in the ratios they use. Under this scheme, the ratio 10:7, for example, would be permitted, but 11:7 would not be, as all non-prime numbers are octaves of, or mathematically and tonally related to, lower primes. Example: 12 is a double octave of 3, while 9 is a square of 3. Uri Landman derived a just intoned musical scale from an initially considered atonal prepared guitar playing technique based on adding a third bridge under the strings. When this bridge is positioned in the nod positions of the harmonic series, the volume of the instrument increases and the overtone becomes clear and has a consonant relation to the complementary opposed string part, creating a harmonic multiphonic tone. Staff notation, originally a system of notation to describe scales, was devised by Hauptmann and modified by Helmholtz, 1877, in which Pythagorean notes are started with and subscript numbers are added indicating how many commas, 81, 80, syntonic comma, to lower by. For example, the Pythagorean major third on C is C plus E, play, while the just major third is C plus E1, play. A similar system was devised by Correlate and used in Barber, 1951, in which Pythagorean notes are started with and positive or negative superscript numbers added, indicating how many commas, 81, 80, syntonic comma, to adjust by. For example, the Pythagorean major third on C is CE0 while the just major third is CE-1. While these systems allow precise indication of intervals and pitches in print, more recently some composers have been developing notation methods for just intonation using the conventional 5-line staff. James Tenney, amongst others, prefer to combine G ratios with sense deviations from the equal-tempered pitches indicated in a legend or directly in the score, allowing performers to readily use electronic tuning devices if desired. Beginning in the 1960s, Ben Johnston had proposed an alternative approach, redefining the understanding of conventional symbols, the 7 white notes, the sharps and flats, and adding further accidentals. each designed to extend the notation into higher prime limits. His notation begins with the 16th-century Italian definitions of intervals and continues from there. Quote, Johnston's method is based on a diatonic C major scale tuned in G, in which the interval between D 9, 8 above C, and A 5, 3 above C, is one syntonic comma less than a Pythagorean perfect fifth 3, 2. To write a perfect fifth, Johnston introduces a pair of symbols representing this comma, plus and minus. Thus, a series of perfect fifths beginning with F would precede C G D A plus E plus B plus. The three conventional white notes A, E, B are tuned as Ptolemaic major thirds 5, 4, above F, C, G respectively. Johnston introduces new symbols for the septimal, and undecimal, and tridecimal, and further prime number extensions to create an accidental-based exact G notation for what he has named extended just intonation. For example, the Pythagorean major third on C is CE plus, while the just major third is CE. In 2000 to 2004, Mark Sabat and Wolfgang von Schweinitz worked in Berlin to develop a different accidental-based method, the extended Helmholtz-Ellis G-pitch notation. Following the method of notation suggested by Helmholtz in his classic, On the Sensations of Tone, as a physiological basis for the theory of music, incorporating Ellis' invention of sense, and continuing Johnston's step into extended G. Sabat and Schweinitz consider each prime dimension of harmonic space to be represented by a unique symbol. In particular, they take the conventional flats, naturals and sharps as a Pythagorean series of perfect fifths. Thus, a series of perfect fifths beginning with F precedes C, G, D, A, E, B, F sharp and so on. For higher primes, additional signs have been designed to facilitate quick estimation of pitches. Sense indications may be added. Downward deviations below and upward deviations above the respective accidental. The convention used is that the sense written refer to the tempered pitch implied by the flat, natural, or sharp sign and the note name. A complete legend and fonts for the notation. C samples are open source and available from Plain Sound Music Edition. For example, the Pythagorean major third on C is CE, while the just major third is CE. One of the great advantages of such notation systems is that they allow the natural harmonic series to be precisely notated. See also, Mathematics of musical scales, microtonal music, microtuner, Pythagorean interval, list of intervals in 5-limit just intonation, list of mean-tone intervals, list of musical intervals, list of pitch intervals, whole tone scale, superparticular number, regular number, hexany, electronic tuner, notes, sources, art of the states, microtonal, just intonation works using just intonation by American composers. The Chrysalis Foundation, just intonation. 2 definitions. Dante Rosati's 21-tone just intonation guitar. Just intonation by Mark Nowitzki. Just intonation compared with mean tone and 12 equal temperaments. A video featuring Pachelbel's canon. Just intonation explained by Kyle Gann. A selection of just intonation works edited by the Just Intonation Network were published on the Telus Audiocassette Magazine Project Archive at Abu Web. Medieval Music and Arts Foundation. Music Novatory, just intonation. Why does just intonation sound so good? The Wilson Archives. Barbieri, Patricio. In Harmonic Instruments and Music. 1470 to 1900. 2008. Latina. Il Levante. 22-note just intonation keyboard software with 12 Indian instrument sounds. Libraria Editrice. Plain Sound Music Edition, G Music and Research. Information about the Helmholtz-Ellis G pitch notation.